Hello students, welcome to the lecture of hydrocarbons. In the last lecture of hydrocarbons, we had discussed about the classification of hydrocarbons, that is the saturated and unsaturated. Within the saturated, there were the compounds which contains carbon-carbon single bonds, that is alkanes or cycloalkanes. And among the unsaturated hydrocarbons, there can be alkenes as well as alkynes, and another type of compounds under the unsaturated are the aromatic hydrocarbons. So, till now we have discussed about the nomenclatures of alkanes and structural isomers of alkanes. Now, besides the structural isomers, alkanes also have stereoisomers in the form of conformational isomers or conformations. Now, we will discuss about the conformations of smaller alkanes like ethane. So, first of all, we need to know what are conformations and why do they arise. So, we know that single bond means there is a sigma bond between two carbons. So, sigma bond has symmetrical distribution of electron cloud around the internuclear axis of C, single bond C. So, since the electron cloud is symmetrically distributed, so if the bond rotates, then also the electrical distribution does not change. So, single bond can rotate almost freely. Due to this rotation, now among the both the carbons have 3 atoms attached to them, that is 3 groups attached to them. So, when the single bond rotates freely, these groups can have infinite number of spatial arrangements. These are called conformers. So, we will discuss conformational isomers. Okay. So, C, single bond C can undergo free rotation. Due to symmetrical distribution of electron cloud. Okay. So, which will result in infinite spatial arrangements of the attached groups. Okay. These are called conformations. These spatial arrangements are called conformations. So, what is the definition of conformations? We can write spatial arrangements of atoms of a molecule that result from rotation of its constituent groups about a single bond are called conformations or conformers, or also called rotamers. Rotamers because these isomers arise from rotation. Okay. So, this is the definition of conformations. Now, for example, imagine that there are 3 groups. Okay. Now, if the rotational axis is somewhere in 3D, like in front of you, that is towards you, then when these 3 groups will rotate, it can be like this, then this. So, 1, 2, 3, it can be like this. So, with every angle there can be a different conformation, and since we know that the number of angles can be infinite, so the conformations will also be infinite. So, infinite number of conformations are possible. Okay. Now, this rotation along the CC single bond is not totally free. So, rotation around CC single bond is not completely free. There is a certain energy barrier. Now, what is the energy barrier? Energy barrier in this case is around 1 to 20 kilojoule per mole. Now, this value 1 to 20 kilojoule per mole is quite small energy. So, to overcome this small energy barrier is very easy for the molecules. This energy barrier arises due to a strain known as the torsional strain. Okay. Now, what is the torsional strain? So, torsional strain can be defined as the strain arising due to weak repulsive interaction between the adjacent bonds. Okay. Due to the repulsion between the adjacent bonds, a small strain occurs. This is known as the torsional strain. Now, how can we predict the conformations? Let us say this is the ethane molecule. Okay. This is the ethane molecule. Now, suppose we keep this carbon fixed, then only these groups will rotate, that is these hydrogens will rotate. So, if we keep this carbon fixed and rotate only the groups of this second carbon, then we will get infinite number of spatial arrangements of these hydrogens with respect to the hydrogens attached to the first carbon. So, we will not write the infinite conformations, we will consider two extreme cases. These are called eclipsed and staggered. Okay. So, these are two extreme cases. Now, what are eclipse and what are staggered conformations? Eclipse means the groups attached to two carbons are closest to each other. Okay. Then we will call this as eclipse, and the second one is staggered. So, you can guess this will be the exact opposite, that is, in the staggered conformation the groups attached to two carbons are farthest from each other. Okay. Now, the conformations can have two representations. One is the sawhorse configuration and other is the Newman configuration. Okay. Sawhorse projection or Newman projection, like this we call them. So, the first one is sawhorse projection. Okay. So, what happens in the sawhorse projection? We represent the carbon-carbon single bond as a longer line which is slightly inclined. Okay. Now, for example, one carbon of ethane is towards you and the other carbon is at the back, okay, away from you. So, the front carbon is at the lower end of this line and the back carbon is at the upper end. Okay. So, front carbon is at lower end, back carbon at upper end. And how are the groups denoted? So, if this is the ethane molecule, okay. So, this is the internuclear excess which is represented by the long line. So, let us say 1 and 2. So, if the 1 is the front carbon, then we can write the hydrogens like this with shorter lines at 120 degree to each other. Groups are the shorter lines. And CC axis is the longer line, and the shorter lines will have an angle of 120 degree. Okay. Now, remember that this is no relation to the actual bond angle. We know that for tetrahedral bond angle is 109.5, but here it is just for the sake of representation. Now, we have to put the groups in the back carbon. Now, there rises the conformations of eclipse and staggered. So, we know that we keep one carbon fixed. So, let us say we keep the first carbon fixed. So, initially we write like this. Okay. If we write like this, then see, this hydrogen is directly in front of this hydrogen. Similarly, this hydrogen is also directly in front of this, and same for the third pair of hydrogen. So, the hydrogens are at a closest distance, that is they are directly behind each other. Okay. So, this conformation is called eclipse. Okay. This is eclipse, eclipsed conformation. Now, how we will write staggered? Same internuclear axis. We will not change the position of the hydrogens in the front carbon. Now, for the back carbon, in case of staggered, it will be the farthest. So, now this hydrogen, the corresponding hydrogen in this carbon will be 180 degree to this. Similarly, another hydrogen will be here and another will be here. So, see, the distance between these hydrogens are now longer than the previous one, right. This conformation is called staggered. Okay. So, this is eclipsed and this is staggered. Now, the second type of conformation is Newman. In Newman, the carbon-carbon bond is viewed head on. That is one carbon on top of the other. Here, front carbon is represented as a point, okay, point, and the back carbon is represented as a circle. Okay. So, this is the front carbon and this is the back carbon. Okay. Now, hydrogen attached to the front carbon will be with longer lines. So, let us say like this, and hydrogen attached to the back carbon will be shorter lines. Now, if we write the hydrogens like this, of course, we cannot show just behind, then we will not be able to write it in 2D. So, we will write this like very close. Okay. That is, these hydrogens are just behind the front hydrogens. This is called the eclipsed conformation. And now we will write staggered. We write the front hydrogens like this, and for staggered it will be exact opposite. That is, for the back carbon the hydrogen will be like this, one is just opposite of this one, the second one will be here, so the third one will be here. This is staggered. Okay. So, we have studied about the configurations, that is conformations of Sawhorse and Newman. In the next lecture, we will study about their relative stabilities. Thank you.